So, we've been constructing truth tables for our propositional statements or propositions. However, one of the most useful, we have been looking at the different truth tables to determine the truth values of our given propositions. This time, to determine whether two propositions are actually saying the same thing or they mean the same thing or not, we can use our truth tables to determine if our propositions are equivalent or not. So we say that two statements or propositions are equivalent if they both have the same truth value for all possible truth values of their simple statements or simple propositions. Equivalent propositions or statements will have identical truth values in the final columns of their truth tables. So, ideally, we would have to construct two truth tables and compare their final columns. However, that will be a little bit too time consuming. Now, take a look at this one. The notation used to indicate that the statements P and Q are equivalent is this one. And we know that this is also used as the symbol for a biconditional statement. So that would mean that instead of creating two truth tables, we can just have one truth table, and the last column will be the two statements that we're going to compare, whether they're equivalent or not, would be the biconditional statement of the two statements to compare. So, we're asked to show that we'll have not P or Q, and not P and Q are equivalent statements. Now, you can do it with two truth tables if you like, but what we're going to have is this one, that we would have to show that not P or Q, and this one equivalent to not P and Q. We would have to find the truth table for this one. Now, what would happen to this one? Remember that these separate would have to have identical truth values at their final columns. So, if we would have identical truth values in their final columns, by the rule of biconditional statement, they would be true. So that would mean that if we're going to combine them into one truth table with the biconditional statement, the column for the biconditional part should always be true. And now that we've cleaned that up, let's now construct our truth table. I'm going to use the alternative method because it's quite faster and more efficient for this one. So I have P and Q, so I'll just have 1, 1, 0, 0, and 1, 0, 1, 0 there. Then, remember, I want to show that they're equivalent, so I will have not P or not, not P or not Q. Then, if and only if, not P and Q. So for P here, I will just copy 1, 1, 0, 0. And for Q, I will copy 1, 0, 1, 0. Now, let's go to the nots. Not P and not Q. So I will use a different color for not P. That's not of this, so not of this one as well. That's 0, 0, 1, 1. And for not Q, it's not this one, so 0, 1, 0, 1. So now I can look for the truth values of the operations in between those propositions. So I will first use this one. So since this is AND, so false and true is false, false and false is false, true and true is true, true and false is false. Similarly, I will have true or false is true, true or true is true, false or false is false, false or true is true. However, in this specific side, I still have to get the not of this entire proposition. So I will just have to reverse this one here. So I would now have not true is false, this is false, true, and false. Now, As you can see, this green one here and this light blue one here, they are the same column. So all we need to do is show that in the biconditional, it will be true. And that's true because in the biconditional, if they have similar truth values, that will be true, this is true, and that is true. So based on this truth table, we can say that this statement and these statements are equivalent, or and writing it as symbols is simply this statement here. So this time you will try. Show that these two statements here are equivalent. The answer will be revealed. So pause the video and try to see whether the two statements are equivalent. So if these two statements are equivalent, then we will have P, or P and not Q is equivalent to P, would be all true. So I only have again two propositional variables. So I will have P and Q, 1, 1, 0, 0, 1, 0, 1, 0. Then I would have this entire statement there, P or P and, oops, sorry. There you go. P and not Q equivalent to P. So for all the P's there, we'll just have to copy that 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. For the not Q, I'll base it here. So I will have, wait a moment. So now I would have 0, 1, 0, 1. And then I would now have to compare that one with conjunction. So true and false is false, true and true is true, false is false is false, false and true is false. I would now have to disjunct that with this one here. So true or false is true, true or true is true, false or false is false, false or false is false. And as we can see, they are again similar. So finally, I will have true, 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 if and only if true is true. True if and only if true is true. False if and only if false is true. And false if and only if false is true. So this is the truth table that shows that these two statements are indeed equivalent. So again, this time, so now show that these two given statements are equivalent on your own, and we'll reveal the answer in the next video.